So, hello everyone. So, in this lecture 4, we'll mainly discuss the distance of a point from a straight line in the Euclidean space V2. So, this is basically the Euclidean, the two-dimensional Euclidean space R2. Okay. So, we'll state a theorem that will give the motivation to define the distance of a point from a straight line. Okay. So let capital L be a straight line in V2 such that every point capital X in L satisfy this equation. So this is basically the equation of the line where P is on the line and N is a non-zero normal vector to the plane. Okay. Then what it says is that you take any point X in L, you can get that norm of X is always bigger than equal to some constant, and that constant is this number. Not only that, this equality will hold if and only if this point will be the projection of P, the point P here, along the normal vector, that is x equals to Tn where t equal to this. Okay. So basically the first picture is basically you have a line, you have the origin, you take x1, x2 or whatever you take this, and d1 is the distance of origin to x1, d2 is the distance of origin to d2. Then basically it says that similarly you take xi, whatever you take, the distance will always be bigger than equal to d. So all the di's will be bigger than equal to d. The second one says that there is a minimum distance, and somehow this gives a motivation to say that that minimum distance will be the distance from the origin to this line. Okay. So what it says, in other words, if you see this picture, so this is the x-axis, this is the y-axis. So you have a straight line capital L, it takes some point P on the line and a capital N to be the normal vector. This capital A is the direction vector of the line capital L. Now you take any arbitrary point X and this is the origin. So we want to understand what is the distance from the origin to the line capital L. So basically first how we do is start, we take some point here capital X, some arbitrary point, and we see that this distance from origin to this capital X is always has a lower bound which is independent of the point. Okay. And it will occur, this distance will be exactly equal to that lower bound which is small d if and only if this x is the projection of this capital P along the vector capital N, along the normal vector capital N. So we will prove this fact and we will define this d to be the distance from the origin to the straight line. Okay. So if x belongs to L, by the given hypothesis of the line, equation of the line, the x dot n equals to p dot n. Now we will apply the Cauchy-Schwarz inequality. In short, we have written it to be CS inequality. So modulus of p dot n equal to modulus of x dot n. Because of this equality, take the mod on both sides. Now by Cauchy-Schwarz inequality, here you apply the Cauchy-Schwarz here, you get that this is less than or equal to norm of x into norm of n. So if you get that norm of x is bigger than or equal to this number, which is nothing but the given number d. Okay, this is the first part. Okay, so this proves the first part. Okay, now for the second part, this is the second part, we want to prove that norm of x equal to d if and only if x is the projection of the point capital P along the normal vector n. So observe that this norm of x will be d. So basically we want to make it equal. Once this is equal, this will also be equal. So once this is equal, we will get this, and once this is equal, that means the equality in the Cauchy-Schwarz inequality holds. That means x will be a scalar multiple of the normal vector capital N for some scalar t. That means that p dot n equal to x dot n, that does not, we have given that p dot n equal to x dot n. Now you put x equal to Tn here, so you will get Tn dot n, which is nothing but t into norm n square, so you will get that t equal to this. So that means we have proved what we wanted, because x equal to Tn and exactly we wanted the value of t to be this. Okay. So now this somehow gives a motivation to define the point from a define the distance of a point to a line. Okay, and we suppose P is on the line capital L. You take any point on the line and you have some q. As long as you know the normal vector capital N to the given line L, you can find the distance from the from that point to that line. Okay, so basically what you have to do, you just I mean, you have to choose that point, you have to choose that point capital X, which will be along, whose direction basically will be along the normal vector, and it should be the projection of some given point capital P. Okay, so this Q, okay, so basically it says that the distance from the origin will be exactly given by this. Okay, so as long as the point capital X is the projection of this point P along n, so basically Tn, where T equals to P dot n by norm of n whole square, then you actually can find this distance, which will be modulus of P minus Q dot n divided by norm of n, and if you put Q equals to 0, you will get exactly d hat d cap equals to d, which is stated in the theorem, in the previous theorem. Okay, so this is somehow the distance between a point and a line, and we'll discuss the application of vector algebra more in terms of plane from the next lecture. So thank you for your attention.